In this video, we're going to discuss the polar form of complex numbers. Remember, the rectangular form of a complex number, z is equal to a plus bi, where the a is the real portion and the b is the imaginary. So what we're going to look at is how to put this into polar form. Now to do this, one of the easiest things to start with is the graph of a complex number. So let's take the complex number z is equal to 2 plus 2i. We're going to graph this on what looks to be the traditional xy axis, but we're going to rename these a little bit. The x-axis now is actually the real axis, and the y-axis we're going to call the imaginary axis. So it is important to note this is not the same as the traditional xy plane. This is an imaginary plane. This is not something we could view on our traditional xy plane. Think of it almost as a third dimension sitting behind that traditional xy plane. But from here, we're going to graph things in much the traditional way. I see that my real portion of my complex number is 2, so I'm going to go 2 ticks to the right. I see the imaginary portion is the 2i, or 2 as well, so I'm going to go up 2 units. And that will be my point right there, where the two meet. Just as another quick example, let's take the complex number z is equal to, we'll do a -3 minus I. So our real component would be -3. I'm going to go 3 units to the left on my real axis. The imaginary is -1, so I'm going to go down by 1. And that would be my point right there. So again, very easy. But we wanted to talk about how to convert these to polar form, also called trigonometric form. The polar or rectangular form of a complex number is this equation right here. Z is equal to r cosine theta plus I sine theta. We see that I popping up there. That is giving us that complex number. It's giving us the imaginary component. The r is what is called the modulus, and the theta is what's called the argument. You may hear them refer to these, so I'm giving you the names. Definitions really aren't real important, or that you know that the name's not really important. It's just helpful to be able to name them. So how do we go from that a plus bi format to this format right here? Well, let's take that first example we graphed, the complex number 2 plus 2i. And I'm going to start with the graph again. I'm always going to do the graph to go between rectangular and polar form. It's very, very helpful. Same thing as we did with just real points. We start with a graph. So there's our point 2 plus 2i. Now what we want to figure out, we want to figure out the r value, meaning the distance from the origin to that point. That should be a straight line. And I also want to figure out the angle that it would take to get there. So I want to figure out this angle right in here. So this will be my r, this will be my theta here. Now, if we look at what we have this side right here, we know that's 2. We also have this side right here, we know that's 2. So we've just formed a right triangle. So if I look at that right triangle, we know 2 of the sides. I know this side over here is 2. I know this side is 2. And so we can use that to figure out the r, the modulus, and the theta, the argument. The r, we can use Pythagorean theorem. We know that r squared will be equal to the 2 squared plus the 2 squared. And so 2 squared is 4. 4 plus 4 will give us 8. And so the r will be equal to the square root of 8. Now, let me add one step in there. We had r squared was equal to 8, and then we took the square root. Typically, when we take the square root, we say we have to put a plus or minus in front. Not true in these cases. The modulus will always be positive, so we're just going to have this positive square root of 8. Of course, we can simplify that to 2 square roots of 2. I also need to get that angle, and of course we know we can get the angle using the tangent because we are given the opposite side and the adjacent side. So tangent theta is equal to 2 over 2, which 2 over 2 is just 1, so we're looking for when is tangent theta equal to 1. And if we think about our unit circle, our special triangles, we know that occurs at an angle of 45 degrees, or pi over 4. We can list complex numbers in terms of either radians or degrees, it does not matter. So we now know the modulus r, we know the argument, we know that it's 45 degrees. Notice it's very important to have this picture because we know anytime we take the inverse tangent or we think about when tangent is equal to a value, there are actually two positions that occurs. In the first quadrant, it's positive 1, also in the third quadrant. So without the picture, we wouldn't know whether we were supposed to use that 45 degrees or if we're supposed to use the 225 degrees. So it's very important to start with that picture. So now I can write my complex number in polar form or in parametric and trigonometric form as z is equal to, r was 2 square roots of 2, r cosine, going to have the 45 degrees in there, and then we're going to have our plus, clear a little bit of room, plus the sine of 45 degrees, which I've put on the screen. So this would be our answer. If we want to convert the complex number to this polar form, we find our r value using our Pythagorean theorem, we find our theta using the tangent. So anytime we want to convert from rectangular to polar form with complex numbers, we can use the equations r is equal to the square root of a squared plus b squared, and theta is equal to inverse tangent of b over a, because the complex number format, a plus bi, gives us the real component, which is the horizontal distance, and the imaginary component, the b component, which is the imaginary distance, that forms that right triangle. The opposite side is obviously the b, the adjacent is the a. So using our Pythagorean theorem, we get the third side, and then by taking the tangent or using the inverse tangent, we get the angle theta. Now just a second ago, we got our answer as 2 root 2 times cosine of 45 degrees plus I sine 45 degrees. And you might be saying to yourself, well, that doesn't look as simple as possible. It doesn't look simplified. That was our final answer because that was that complex format that we talked about. We want the r cosine theta plus I sine theta. But let's see what happens if we simplify it. Let's see what happens. Well, we know that the cosine of 45 degrees is root 2 over 2. We know that the sine, cosine, in fact, both the same. They're both root 2 over 2. So we'd have 2 root 2 times 2 over, root 2 over 2 plus I sine of 45, which is root 2 over 2. Next thing I'm going to need to do is distribute that through. Well, first thing I see that happens, I see all these 2's outside the radical just cancel. If we were to distribute, all those 2's would cancel, and so then we'd be left with root 2 times root 2, which is just 2. And we'd have root 2 times I, root 2, which is just 2i. And that's exactly where we started. That was the rectangular format of the complex number. So to convert from polar to rectangular form, it's very simple. We just multiply the equation back together. So here's the statement: to convert from polar to rectangular form, complex number, evaluate trig functions, and then multiply. Let's do one more example. Let's take that second example that we drew out. So the complex number we had in our second example is z is equal to -3 minus I. Let's convert this to polar form. So the first thing that I'm going to do, once again, is draw the picture. Now I know we've already done it, but it's always a good idea to draw the picture. Just a little sketch to make sure I have it in the right quadrant. Left 3, down 3, so it's right there in the third quadrant. That's going to be important. So to find my r, I'm going to take the square root of -3 squared plus the -1 squared. And -3 squared is 9, -1 squared is 1. When I add those together, I get the square root of 10. Easy enough. Next, I want to find the theta. And again, we can, even though it's in the third quadrant, we can still view that as a right triangle. So that's why the r is still just using Pythagorean theorem. Theta is still just going to be the inverse tangent of the b, the opposite, we can see the opposite's this side over here, that was the -1, over the a, well that was the -3. So now we'll go pull up our calculator. All right, so now I have my calculator up. I'm going to take my, first thing I'm going to do is check my mode, make sure that I'm in, we'll do this one in degrees mode again, but we can do it in either. Make sure I'm in degree mode, then I'm going to take my inverse tangent, and my numbers, remember, were the -1 over -3. And the reason I'm using my calculator on this one is because we don't know what the 1/3 is. We can simplify it to 1/3, but we don't know when tangent is exactly 1/3. So we see that it's this approximate number, 18.43. So I'm going to write that down for 1 second. 18.43 degrees. But then this is why the picture is so important, because if I look at 18.3 degrees, that would be up here, and that's obviously not where we want to be. Remember, inverse tangent, anytime we use that feature in the calculator, it is giving us the one position that the inverse tangent can exist, which is in the first or fourth quadrant. But of course, we need this to be in the third. So I'm going to take 180 and add that to it. If I take 180, add it to the 18.43, I get 198. 98.43. And so that will be my angle. Now that I have both of those, I'll put it together in my complex number form. And there it is. Our complex number is equal to the square root of 10 times cosine 198.43 plus I sine 198.43.